Okay, so now we're really going to start looking at where we can really start to see some very calculus-y concepts starting to emerge. And some of these people, your calculus textbook talks about various things that Fermat has proven, and we're going to sort of talk about some of those things right now. So a little bit of background information. There's a lot of people involved going from where we were to where we are now, people that are mentioned in the book, people that we're not going to mention, just a whole bunch of people. But I want to sort of key in on two different people, Fermat and Descartes. Now, I wouldn't say that these two guys were rivals, but they were both doing similar things at a similar time. One kind of maybe outdoing another in different cases, and kind of maybe going back and forth like that. But they were both interested in analytic geometry. Now, I don't want to get into too much about exactly the precise definition, but the basic idea is that we are going to now move from just purely geometry and purely algebraic things to combining these two things together into what's called analytic geometry. The reason maybe that we call this analytic geometry is due to sort of the Greek method of analysis. In a certain sense, it might make, calling this algebraic geometry would also be appropriate, but that sort of means something different now. Anyways, so analytic geometry, what we're thinking about is, if we think back to sort of the word problems that we were talking about before that sort of motivated study of algebraic equations, we're going to now connect this to geometry. So now if we call our unknowns, by letters x and y and things like that, we can think about these equations as defining curves on a surface or on the plane. So the story goes that Descartes one day was laying in his bed and looking up at the ceiling, and he saw a bug crawling around on the ceiling, and he realized that, if you picked some location as the origin, then every location of this bug could be described by two different numbers: how far it is along the x-axis or the horizontal axis, and how far along it is along the vertical axis. And so this kind of motivates his study of geometry and equations, or not motivates the study of those, but sort of the connection there. In the sense that if you take you take an algebraic equation, x squared plus y squared is equal to 17, you can now plot the points in the plane that satisfies that equation, and that gives you a curve. And so now there's this vocabulary, this dictionary to go back and forth between algebra and geometry. And as we will see, this sort of helps a lot. Going forward, this helps a lot. Now, Fermat and Descartes both had kind of different ideas, slightly different approaches and how to do things. Fermat kind of realizes that an equation in two variables gives a curve, so he's more sort of algebraically motivated, and Descartes kind of goes the other way around. But I don't want to get too much into the intricacies between their disagreements. As we will see, well, maybe I'll mention to it if I remember when I get to the slide. So the first thing that I want to talk about, mainly the main thing that I want to talk about for this video, is this concept or this procedure that Fermat has called adequality. Now, I'm not exactly sure how to say this name. So the word here, the verb is adequate or adequate. I'm not sure which one is the correct one to use. I'm going to say adequate because I think that sort of makes sense. Here's what we want to start with. So Fermat remembers the following fact from Viette that we haven't talked about yet, but you can read about it in the book. And it says the following: if we have the equation, let me make sure I'm in the frame here. If we have the equation bx minus x squared is equal to c, we're interested in several things. One of the things that we're interested in is the maximum value that c can have. And another thing that we're interested in is what relationship do the roots to this equation have. Okay. In other words, if b and c are fixed, so throughout this video, or throughout this example, really, we're going to sort of change our perspectives every now and then. So we can think about B and C as being fixed and solving for X, or we can think about, the left-hand side being a function and then wanting to figure out what the maximum value, the maximum value is, that is the biggest value that C can be. But if we think about B and C as being fixed, then we can solve this. We get two roots, x1 and x2. These are two different solutions. I should say two different solutions to this equation. Now, what was observed by Viette is that if we plug in x1 and x2, we're going to get bx1 minus x1 squared is equal to bx2 minus x2 squared. And again, yes, okay, just making sure that I'm in frame here. Now, if we move this, if we subtract this over here, what we're going to get is b x1 minus x2 minus x1 squared minus x2 squared is equal to 0. Now, both of these have a factor of x1 minus x2. So if you divide by x1 minus x2, divide here by x1 minus x2, divide here by x1 minus x2, what we're going to be left with, this is going to be equal to b. And then when we do division here, this is just going to be x1 plus x2, and that's going to be equal to 0. So in other words, what it says is that if you have two solutions to this equation, x1 and x2, then x1 plus x2 is equal to b. Okay, so if we have two solutions to this equation, x1 plus x2 is equal to b. Okay, so let me just record that information up here. X1 plus x2 is equal to b. Now this line and the slide got cut off a little bit. Sorry about that. Maybe can I move it over? Yeah, this is what it says. Okay. So what is the motivation for setting an equation like this? It's not so important for what we're going to talk about here, but the motivation is if you have a line of length b and you want to cut it at a point x, then this is going to give you the product of the two different parts of that line. So if you have a line of, let's say, you have a line of length b and you cut it at x, then this length, this is b, this is length x, and this is length b minus x. The product is going to be equal to b minus x. B minus x times x is equal to that. And so the question is, what does x need to be in order for their product to be equal to c? And then a related question is, for all of the different values of x, what is the biggest one? What's going to give me c here? Now, by symmetry, it would appear, and this turns out to be correct, that x would have to be b over 2. Because, well, just again, I'm just going to say by symmetry and let you guys fill in the details, that x would have to be equal to b over 2. And then if you plug in b over 2 here, then what you get is, as I say here, as I wrote here, Fermat knows from Euclid that the maximum for this is b squared over 4, which again is what you get if you plug in b over 2 here. Okay, so let's keep this in mind, but let's now change our perspective just a little bit. And let's think about if we were to move the c over here. We're going to have bx minus x squared minus c is equal to 0. Now, if c is the biggest that it can be over here, how that equates here is that the biggest c can be here. So now here, if we just look at this, c can be any value that we want it to be. Okay, if we're not viewing it as a, in this setting here, c can be whatever value you want it to be. It could be, there's no largest value that c can be over here, but there is a largest value of c such that the left-hand side is still positive. Okay, so let's look at a graph of I've got a graph here, 4x minus x squared minus c. That's the graph that I have right here. So this would correspond like to b being equal to 0, or sorry, b being equal to 4. And so now we can see what happens. If c gets bigger and bigger and bigger, this curve comes down, and eventually at the biggest c can get, it's going to touch the x-axis, and at that point, for that value of c, we now have a double root. That is, we have a root with a multiplicity 2. In other words, the two roots are equal to each other. Okay, so what can we do with this information? Well, if we think about an equation like this, and again, we have two different roots. We're going to have bx1 minus x1 squared is equal to bx2 minus x2 squared. Now I want to think about, I'm not going to write this dependence explicitly, but x1 and x2 both depend on c. Now let's think about what's going to happen here. As we make c get bigger and bigger and bigger, x1 and x2 are going to go to each other. They're going to approach each other. Okay, so what I'm going to do is I'm going to divide both sides of this, again, like I did before, by x1 minus x2, x1 minus x2. This is exactly what I did before. And if I rearrange, we're going to get exactly what we got before, which is going to be b x1 minus x2 over x1 minus x2, and then minus x1 squared minus x2 squared over x1 minus x2, and this is equal to 0. Now if we think about changing c so that c is getting closer and closer to its maximum value, so that the left-hand side here is positive, as c approaches that value, whatever it happens to be, I mean, we know in this case it's equal to 4, but let's imagine we don't know what it is. As c gets closer and closer to that value, it means x1 and x2 are getting closer and closer to each other. Because again, x1 and x2 are the zeros of this equation, and so again, they depend on c, right? x1 and x2 depend on c. And so what happens as we think about moving c here, the values of x1 and x2 are changing, but we see what's happening. They're getting closer and closer to each other. This is x1, that's x2. And so they're getting closer and closer to each other. Okay, well, what we formed over here is just the difference quotient. And as we imagine c getting closer and closer to its value, to its maximum value, its maximum value such that the left-hand side is positive, you know, geometrically what's happening here, or graphically what's happening here, it's going to the point where we're going to have a double root. In other words, x1 and x2 are going to each other. So what's happening, again, one more time, x1 and x2 depend on c. I didn't write that dependence explicitly. You know, maybe we could like write a superscript for c or something like that. But what's happening is we're taking the difference quotient and making x1 and x2 go closer and closer to each other. So it's equal to 0. So essentially what we're doing here is we are looking at the derivative and then setting it equal to 0. That's one way to think about this. Obviously, this is not the exact way that Fermat was thinking about it. Okay, well, he was able to take this idea and run with it and really do some amazing things with it and really get to the definition of a derivative without calling it that. Okay, so let me make sure that everything is in frame here. So unfortunately, I'm now realizing let me see if I can fix this in the middle of the video. My writing is a little bit bigger than I expected it to be. Okay, so let's look at this a little more generally. Let's imagine we have, I'm going to sort of illustrate this with a quadratic polynomial. P of x is equal to ax squared plus bx. And then we want to know what the maximum value of this is. Really what we want to know is the location, the x value that gives the maximum value. And really when we say maximum value, A and B here are positive, but if A and B could be negative, when we say maximum in particular, if A could be negative, by maximum value we mean like a local extreme value. But for now, let's just think about maximum value. Okay, or again, this would be for this one in this form right here. This would actually be the minimum value. So sorry about the confusion there. Anyways, so and we don't care about the maximum value or the minimum value precisely. We care about the location, because if we add a plus c here, it's just going to change the value of the maximum value, but not the location. That is not the x value of the maximum value. So we're going to look at something like this. And then if we set this equal to c, we can again write this as ax squared plus bx minus c is equal to 0. And we're going to have a very similar thing happen. I want to know what the biggest value c is here, or equivalently what the biggest c value is here. And if I look at roots of this equation, that is where you plug in x1 here and you get 0, we've got p of x1 is equal to p of x2. And then if we subtract and divide by x1 minus x2, we got p of x1 minus p of x2 over x1 minus x2, set that equal to 0. Well, again, conceptually, if we think about what's happening here, we want to think about c going to its maximum value. As c goes to its maximum value, x1 minus x2 are going to each other. So now what's going to happen here? This is a polynomial. We're dividing by x1 minus x2. You might, we'll look at an example in just a moment here. What's going to happen here, okay, is that the x1 and x2 is going to cancel with stuff that you have up here. So the x1 and x2 are going to cancel with stuff that you have up here. Now, as x1 and x2 go to each other, they're going to be the same value. And so you just, wherever you see an x1 or x2, you just set that equal to x, and then you solve this resulting equation for x. Okay, so let me explain this with this example exactly. So if I look at my p of x, I'm going to do p of x1 minus p of x2 over x1 minus x2. And again, as we think about as c goes to its maximum value, x1 and x2 are going to go closer and closer to each other. So as this c goes to its maximum value, if we think about moving this c to its maximum value, x1 and x2 are going to get closer and closer to each other. So what's going to happen here? We're going to have a times x1 squared minus x2 squared plus b times x1 minus x2, and we're going to divide by x1 minus x2. And again, x1 and x2 are the solutions to this equation for a given value of c. So p of x1 is equal to p of x2, so then this is equal to 0. Now notice what happens over here. x1 squared minus x2 squared divided by x1, x2, we're just going to be left with a times x1 plus x2, and then over here we're going to be left with plus b, and that's equal to 0. Okay, now again, notice what happens. x1 and x2 are solutions to this equation. So when c is either at its minimum or its maximum value, I keep saying maximum, but in this case it'll be its minimum value. When c is the smallest that it can be, x1 and x2 are equal to each other, because again, when c is as small as it can be, what we're going to have for the ax squared plus bx minus c, for that polynomial, is going to be exactly where the vertex of the polynomial touches the x-axis. In other words, we have a double root, so x1 and x2 are equal to each other. So then if x1 and x2 are equal to each other, what this tells us is 2ax plus b is equal to 0. In other words, x is equal to minus b over 2a, which is exactly what we know where the vertex, the x value for the vertex of a polynomial like this. Okay, so that was what Fermat realized, but he realized that you can do this not just for polynomials, not just for a quadratic, but you can do this for any sort of polynomial. Okay. So if we think about this polynomial that I have here, for the example x cubed minus x squared minus x, let me graph what's happening here. So now we have something a little more subtle. Now we have two different points. So again, what Fermat's method does is it finds the local min and the local max. And the reason that it does that, once again, is because if I adjust my value of a here, I'm calling it a instead of c. Okay, when we just get it, so that is just touching the x-axis here, what this means is we're going to have a double root. We've got a double root here and just a single root here. So we're going to have a double root here. So if I have an equation x cubed, so again, I just want to point out that x cubed minus x squared minus x, if I want to find the value of a that maximizes this, okay, it's an equivalent, sorry, this should be cubed. It's equivalent to finding the largest value of a such that this is still positive. Anyways, so if you look at something like this, now what happens if we imagine two different zeros. So we've got x1 cubed minus x1 squared minus x1. Hold on a second here. Equals x2 cubed minus x1 cubed minus x2. Sorry, this should be a2 here. And again, I'm not giving formulas for x1 and x2. It doesn't matter. Like, we don't need a formula for them to know what it happens. But what we're imagining here is making x, having a be a local maximum, a local minimum or a local maximum. Because again, if we find a local min or a local max, what it means is when you write it in this form right here, we're going to get a double root to the equation. So x1 and x2, if a is a local maximum or a local minimum, because of because what it means for their local min or local max to intersect the x-axis, it means there's a double root there. Okay, in other words, the two roots are equal to each other. All right, now if we rearrange this, what we're going to get is x1 cubed minus x2 cubed minus x1 squared minus x2 squared, and then minus x1 minus x2. This is equal to 0. And again, just like before, we're going to divide by x1 minus x2. Okay. So I just left my notes somewhere. I want to make sure I say everything that I need to say here. Okay, yeah. Now, x1 cubed minus x2 cubed. Just to remind you, this is x1 minus x2 times x1 plus x1 x2, or sorry, x1 squared plus x1 x2 plus x2 squared. Sorry about that. And so now, And so now what happens when we divide by x1, x2, I'm just going to do this here, the x1, x2's cancel, and we're left over here, for this one, we're left with x1 squared plus, x1 squared plus x1, x2 plus x2 squared. And then when we do this, we're just left with plus x1, x2. Minus x1 plus x2. And then over here, we're just left with 1. That's equal to 0. Now again, if we are looking at a local minimum, then if A is a local minimum, then this right here, it means that x1 and x2, it means that this is going to be equal to 0. So again, if A is a local minimum, we rearrange, this is going to be equal to 0. However, whether or not A is a local minimum, if we put A over here, if we have a solution here, and then we move A over here, this is going to be equal to 0. But in the case that A is at a local minimum, again, it means we're going to have a double root. Okay, so I got two solutions, at least two solutions to this equation here. If I move it over, I'm going to have two different solutions. But I want the two solutions as if A is a local minimum. If we're at a local minimum or a local maximum, what's going to happen is that x1 and x2 are equal to each other because we have a repeated root. So in other words, if you put x1 and x2 equal to each other over here, this is going to give us x1 and x2 are equal, so this is going to be x squared plus x squared plus x squared. So we're going to get 3x squared minus 2x minus 1 is equal to 0. And again, that's just the derivative that we see over here, and we're setting it equal to 0. Of course, they're not calling it the derivative, but this is just the method, this very geometric method that Fermat found to be able to, or this very analytic geometrical method to be able to find locations of maximum. So there's a conceptual question that is one of the ones that's going to be, there's a conceptual question. It's something that's going to have to be sort of wrestled with later on when in more calculus-y sort of situations. Notice that we are dividing by x1 minus x2, doing some algebra, and then setting x1 equal to x2. Okay? In other words, if you go back to the beginning, it's like we're dividing by 0. So that is a conceptual question that's going to have to be tackled, and the ultimate answer is going to involve limits. Okay, so one of the next methods that Fermat does, I'm just going to mention a little bit briefly about this. Instead of calling the two roots, x1 and x2, he just calls them x and x plus e. And then he has this idea that he has been using called adequating. So we're going to equate, if you have a polynomial, p of x, we're going to say it's approximately equal, or not approximately equal, but adequate. They're not equal, they're equated to p of x plus e, and we're going to subtract and then divide by e, so we're going to end up with something like p of x plus e minus p of x over e is equal to 0. And then again, what we're doing conceptually is letting e go to 0. So again, this is a difference quotient. He doesn't talk in terms of letting e go to 0. He just says we're going to do whatever, e is not equal to 0. We're going to do whatever algebra needs to be done here. Having it equal to 0 is going to give us some relationship between the roots and the coefficients. And then we're going to solve for, then we're going to set the two roots equal to each other. We're going to set e equal to 0, and then see what that tells us about x. And that's going to give us the locations of the local mins and the local maxes. Okay, but again, we can see here we've got the difference quotient here explicitly, though I don't think he's calling it that at the time. Okay. So Fermat says about this, we can hardly expect a more general method. That is, a more general method for finding local mins and local maxes. And in essence, he's exactly right about that. Okay, now he's kind of only dealing with polynomials, but this is sort of the most general method that we have for finding minimums and maximums. Okay, so the next thing that I want to do is to discuss tangent lines. So he was also able to use this method, this adequation method, this adequality method, to find tangents, which makes sense to us because what we just wrote down is the derivative, and the derivative is sort of initially defined as the slope of the tangent line. So it makes perfect sense for us that this should somehow be evolved, that he should be able to use this method to find derivatives or to find tangent lines. So I'm going to go through how he does this. I'm going to have to turn on. I have this example here as just a generic curve. There's nothing special about this curve. It just kind of looked like what I wanted it to look like. So we have this point B. We want to find the tangent at that point. Okay, so here's how we can do it. Okay, now essentially what we want to do here is we want to figure out what the point E is. So this is the point on the curve. The point on the curve is 3.5, and then f of 3.5. That's what this point is here. 3.5 f of 3.5. Then if we know what E is, that is where it intersects the x-axis, we've got 2 points on a line, and we know that the y value here is going to be equal to 0. And if we know what the x value is, then you've got 2 points on the line, and we can then compute what the line is. Okay, so let's see here. Let me move this slider for A a little bit down here. Okay, so what we're going to do is the following. Okay, we're going to think sort of in terms of similar triangles. So notice this purple line is the tangent line. So in terms of similar triangles, we know that AI, so this triangle going AIE is similar to the triangle BCE. So the triangle AIE is similar to the triangle BCE. Okay, so then what we know is that these ratios are going to be equal to each other. Let me get this so I can say it exactly without making a mistake. Okay. So what we know is that AI over EI, we know that AI just again based on similar triangles, we know that AI over EI is exactly equal to BC over EC. Okay, so we know AI over BI is exactly equal to, so AI over EI is exactly equal to BC over EC. Okay, so what I want to do is this distance from from E to C, I'm going to call that distance from E to C, I'm going to call that T. So EC here, we're going to call this T. Now what is BC? Well, BC is just going to be f of this point. So the coordinate for x, I'm just going to, b here, it's equal to 3.5, but I'm going to call it x. So the distance there, BC, is just equal to x. So this is equal to f of x. Okay, now AI is whatever that distance is here. If we knew what A was, like if we knew the x coordinate for A or something like that, if we knew the coordinates for A, then we could just use that as a point. So we don't know what A is. We know what the x coordinate for A is. It's just whatever we want it to be, okay? But we don't know what this point is on the tangent line because we don't know what the tangent line is yet. Okay, but we know that EI is this distance here. Now this distance from C to I, we're going to call that E. That's going to be our lowercase e value. So before in the board before we were doing x and x plus e. So we're going to call this distance right here E. So what this means is that EI is going to be equal to T plus E. So this is T plus E. Okay, now here's where the non-equality will come in. So we're going to replace the non-equality with a wiggly equals because AI is approximately equal to FI. AI is approximately equal to FI. So these two are not equals, but they're there's an adequality. Okay, they're close to being equal. But now what is FI? Well, F here, this point, is just F of x plus E. So C here is x, that distance there is x. And so that, that point there, the vertical coordinate, the y coordinate, is just f of x plus e. So we've got f okay, and so now what Fermat does is he does the normal thing with the adequality is he equates them, does the algebra to figure out what t satisfies when e is equal to 0, and that's going to tell us, again, t by definition is the distance from there to there. And since we know what x is, then we can therefore figure out e from that. Okay, so what this gives is t of f of x plus e. Again, using his notation, he would write this as t plus e f of x. Now from this, you figure out some properties that x satisfies. So for example, let's say, for this example here, I say let's do this where f of x is equal to the square root of x. So let's do this. If f of x is equal to the square root of x, then what we're going to have is t times the square root of x plus e is equal to t plus e times the square root of x. If we square both sides, we're going to get t squared x plus e is equal to t plus e squared times x. And now what we want to do is we want to solve this for x. So notice if we divide both sides by x plus e, we get t squared is equal to, this is just going to be, sorry. Yes, okay, that's quite right. If we take e equals to 0 now, we're going to get t squared x is equal to, hold on, I've made, yes, okay, whoops. Okay, so over here, sorry about that, we're going to get t squared x plus e, and over here we're going to get t squared x plus 2t e x plus e squared x. Okay. Okay, so sorry. I'm going to move this up here because I'm getting a little... Okay, so notice I've got a t squared x and a t squared x. So on the left-hand side, I've got t squared e. And then on the right-hand side, I've got 2t ex plus e squared x. And now if I divide, if I factor out an e from both sides, I'm going to get t squared. Or if I divide by e on both sides, I mean I'm going to get t squared is equal to 2t x plus ex. But then again, remember the whole idea is that e is going to get closer and closer. Like if we go back to the image here, if I can find it. Okay, as a gets closer and closer to 3.5, remember e is this distance here, so e is going to 0 because these triangles, the equality we started with is approximate here, but as a goes to f, we get something that's closer and closer to an actual similar triangle. E is going to 0. And then, so what this gives us is, in the limit, that's not how he said it, but how we would say it, as e goes to 0, we just forget about this term here. We're going to get that t is equal to 2x. And from this, you can figure out what the slope of the tangent line should be. Okay, anyways, so that is it for Fermat and Adequality. What we have for his method of, again, his method of Adequality is getting very, very close to sort of just explicit calculus things that we're dealing with. There's a couple of things that he doesn't quite have in place, but he's got a lot of the building blocks there. And we're going to see how there are more building blocks developed. And then, once we get to Newton and Leibniz, and a little bit even past with, definitely once we get to Newton and Leibniz, we're really going to see how they took some of these ideas and sort of ran with them. But okay, that's it for this video. Sorry, it got a little bumpy there. I'm trying to do, as you can see, I'm trying to do something a little bit new, and so trying to have things, set up properly is getting a little distracting.